are now recording. I am going to set this up so I can scroll all over the screen and drive you all crazy with that. There we go. Yeah. Now we can do happy faces and all that good stuff. All righty, let's jump right in. The immune system. Now, I'm sure if you were all reading the chapter, you know that it can be a little on the confusing side. And we got D cells, B cells, memory cells, preceptor cells, suppressor cells, cytotoxic cells. You know, what I'm going to try to do is just to kind of try to simplify it a little. Now, I do want to remind you that everything that you will see on quiz number 2, you will see on this PowerPoint. And I put this little guy, he's my angry germ. I call him my angry germ. If you see him, you might see it again. So, well, we're going to start off with the nursing concept. The nursing concept of immunity just refers to the body's, how the body responds to infection and disease. Not much else to say right there, but you might see that one again. Moving on. Now, like I said, it can be a little confusing what all the different cells do, the macrophages and the etc. So all you have to do is memorize this chart and you got it made. Any questions? I'm joking, right? You all know I'm joking. Let's simplify it a little bit more. The immune system basically consists of 2 parts. One of them is the innate or the non-specific, and they just basically go out and kill everything. Something shows up in your body and your body doesn't recognize it, it kills it. This system can also apply to if you have a not transfusion, but a transplant. If they put somebody else's liver in you and you're not using any medications to suppress that immune system, your immune system will attack it because it recognizes it as a foreign thing. So it uses a thing called histocompatibility markers. Yeah, I'm not expecting you to memorize that or anything. Usually the histocompatibility marker is like the cell's fingerprint. So when these things go looking around, they're just they're checking for that marker. The adaptive or the specific immune system, that's where we get in the T cells and B cells. They're a lot more particular. They're the ones that actually look for specific pathogens. For example, you've had the measles before and you get a measles germ in your body. These are the guys that go around looking for specific germs. That'll be really relevant when we start talking about COVID. Let's look at the innate system first. There again, this is just a reminder, the innate system kills basically everything and the adaptive targets particular cells. The innate or the non-specific, there's 2 parts to that. One of them is the external. And the external is pretty common sense. You know, it's just your skin, your mucus. Your skin is the largest organ in your body. That's your first line of defense right there. I mean, that's like the castle walls. That's keeping out the majority of everything. I mean, every day we're totally bombarded with crap that wants to kill us. That's just, our body is constantly at war. Hence the military theme. Anyway. The mucous membranes, there's openings in our castle wall, you know, our mouth, sexual organs, rectum, ears, nose, and each one of those has their own line of defense. The the mucous membranes in the various parts of the body contain either acids, like your stomach. The acid content of your stomach is almost the same pH as sulfuric acid. So that's one of the first lines of defense against pathogens trying to get into your body. And then other parts of your body, like your digestive tract, through your rectum, there are bacteria that are a part of our healthy, they're not the bad bacteria, they're the good bacteria, and they kind of help as a defense against infection as well. That's why when antibiotics go through your body, they kill off the good bacteria as well as the bad bacteria. It opens you up for things like yeast infections, et cetera. So those, the different mucous membranes throughout the body are kind of another line of defense. When we look at the internal defense system, that's when it starts to get more interesting. These are the cells that break down. There was a nice little chart in your book that shows how a monocyte, which is almost like a mast cell, or actually it's like a stem cell. We all hear a lot about stem cells. Stem cells can become anything they want to be. The monocytes are like a stem cell. They can change into a macrophage. They can change into a dendritic cell or whatever. But basically, there's 4 guys in the innate system that run around your bloodstream. Now, we're all kind of familiar with the neutrophil. Y'all were studying that under Bill. That's one of the white blood cells. In fact, when you get a cut and you develop pus, the pus is actually the dead neutrophils. They race to the site, they eat all the bad stuff they can, and then they die. They're a one and done. That's basically it. But they're also the most abundant in your body. So if you have an infection and the neutrophils are racing there and they're eating the bad guys and dying, you're going to develop pus in that wound. Nice breakfast time discussion. The other one is macrophages. Macrophages come from monocytes, and they consume, but they, that was an interesting one. They consume, but then they continue. I mean, they can eat multiple pathogens and they spit them out. They basically kill them and then they spit the parts out. And that becomes significant because the dendritic cell over on the other side there will come and and use that to transfer over to the adaptive immune system. We'll talk about that when we get to the dendritic cells. But these guys can eat multiple times before they die. I can't remember what the number was. But both of these guys are phagocytes. Phagocytosis is the process of basically just consuming something and killing it. Now, these guys have a hefty appetite. There's another one that's a part of this system. It's called the natural killer cell. The natural killer cell is a little more specific. This is the one that usually will go after viruses and cancer cells. Now, if you've read along in the chapter, you might see, well, I mean, don't the T cells do that too? The natural killer cells aren't as smart as the T cells and B cells, but he'll go along and remember I told you the histocompatibility markers. There's a little marker on your cell called MHC1, which stands for Major Histocompatibility Complex. But it's a histocompatibility marker. And basically that's like your cell's driver's license. When the natural cell walks up, if your cell is healthy, it'll have an MHC1 marker on it. If the cell gets unhealthy, these markers just kind of shrivel and they're not doing their job. Then the natural killer cell will come along and look at that and go, oh, you're not healthy. Then it injects some poison into that cell and it kills it. So they're just kind of a general assassin, so to speak. But they do have some similarities to the T cells as well. Anything out there? There's something else about the natural killer cells I wanted to tell you, but I can't remember what that is. That's pretty much it, I believe. Now we have this other guy down here, the dendritic cell. I don't know why it's doing that on the screen, but oh well. Better not use this thing. Dendritic cells are they are the messenger between your innate immune system and the adaptive immune system. Remember when this monocyte was running, or monocyte, yeah, I'm sorry, this macrophage is running around consuming these pathogens and spitting these pathogens out. He's spitting out parts of the pathogen markers. Well, the dendritic cell comes along and picks up those pathogens, and then he grabs them and he runs over to the adaptive immune system and he gives them to the T cells and the B cells. Now, I think it's the B cells that is the one that it runs to, but the dendritic cell is the messenger. It goes back and forth between your non-specific and your specific immune system, your innate and your adaptive immune system. So good to think of him as just a messenger. In fact, I think I got, I got more down here. Okay, I talked about that. Here we go. Takes old parts from defeated enemies and creates antigens and gives those antigens to the adaptive immune system. And here's a good example right here. Phagocyte, like a neutrophil or a macrophage, consumes the bad guy, and then he spits these parts out. And the dendritic cell grabs these parts. I'm having a hard time figuring out which one's the phagocyte and which one's the dendritic cell. Anyway, this phagocyte eats the bad guy, spits the part out, and then the dendritic cell takes that part and gives it to the helper T cell right here. And then that helper T cell runs back to all the other T cells and gets your adaptive immune system going. So it's just good to remember that the dendritic cell is a messenger between the two. Phagocytes are neutrophils and macrophages. Oh, I got my little guy up here. As I say, wait a minute, where's my guy? Oh, he's just hanging out up here in the corner. These are things you want to remember. What phagocytes are, they eat the bad guys, and that includes neutrophils and macrophages. And the dendrites are the messenger between the innate and adaptive immune system. Nod, nod, wink, wink. So that pretty much summarizes the innate immune system here. Are there any questions on that before I go on to the adaptive immune system? No?
No, thanks.
No,
All
thanks.
clear as mud, right?
Clear-ish.
Clear-ish. We're getting there. Okay. Things get a little more confusing in the adaptive because each of the B cells and each of the T cells breaks down into several different subcells. And we're not going to go into intimate detail on all those. Did any of you watch the videos that I had posted about the immune system? I can't remember the guy's name, but I got 3 videos in there and he's very funny and he talks about the immune system. What was that guy's name? Anyway, I posted it under your resources for week 4. He goes probably into a lot more detail than we're going to need, but he is very entertaining. So he's kind of fun to watch. And I'm going to use his videos a lot in my teaching because he's funny. Humor's a great way to learn, right? So moving on, let's look at the adaptive. As we all know, there are B cells and there are T cells. Now, why is this information important at this point in time? Anybody know? Anybody got a guess?
COVID.
COVID, bingo. you get the silver star for today. COVID. When we talk about COVID, we are talking about B cells and T cells. COVID is a virus. It's a very sneaky and clever virus. It sneaks into your body and it pretty much eludes your general or innate immune system. So it's up to the T cells and the B cells to hunt this guy down. And they have a secret weapon called antibodies. Now we're talking a lot about antibodies and antigens. This is a good diagram to kind of illustrate what the difference is. Antigens are parts of the bad guy, and each bad guy looks a little different. This may be measles, this is smallpox, this could be COVID, and this could be polio over here. So each antigen has its own little markers, and the body, the B cells, will create antigens to recognize each of those. So if this is an antigen for measles, it's only going to recognize the measles. If this antibody runs into a COVID virus, he's not going to do anything. And I'm going to show you here in a minute why this is important, that these two can connect. Right now. The antigens, once the B cell has produced antigens against, or antibodies against a certain antigen, they can connect. And when you have this bad guy hanging around in the body, let's call it measles, the antibodies for measles will attach to these. Now, when the antibodies attach to the cell, it's doing a couple things. One of them is it's signaling to the rest of the immune system, especially the phagocytes, saying, hey, this guy's a bad guy. Come get him. Come eat him. And they kill off the bad guy. What they can also do is they can all cluster together into a larger agglutination, a larger ball, which then makes it easier for the phagocytes to find and consume. And as long as these guys are covered in antibodies, they can't attach to the healthy cells of your body and cause problems. Because as we all know, I probably know what a virus does. It attaches to a cell, it inserts itself into the cell, it goes to the nucleus, it takes over the DNA, and it begins replicating additional viruses in the DNA. So the antigen has to connect to a body's cell. Well, if this antigen is surrounded by antibodies, it kind of prevents it from connecting to one of your healthy cells. So the antibodies do a couple of things. The most important is signaling your body to let the other cells, the killer cells of the body, both your innate phagocytes and also the T cells, help the T cells come in and wipe them out. I've got my notes hanging out here. There we go. So moving on. Okay, something you want to remember, agglutination, the process of antibodies attaching to antigens and clustering for phagocytosis. Clear as mud, right? You got it. Moving on. Well, looking at the adaptive immune system, we have the B cell. The B cell is in the humoral system, humoral meaning blood. It's in the bloodstream. Your B cells travel around. This is kind of like the outer perimeter. And there are two different types of cells. I think there's more than two, but the two most important ones, or the two general ones that I want you to remember, are the plasma B cells and the memory B cells. Now, the plasma B cells are extremely important because the plasma B cells produce the antibodies. So when we create a vaccine, like the COVID vaccine, I'm going to bounce back here a second. Let's say this is COVID right here. What we do is we create an antigen that looks like COVID. Now, as y'all probably know, vaccines historically, I'll just tell you a little war story here. The first vaccine actually was in the 1700s. Smallpox had a tendency to go through countries and ravage them. I mean, smallpox was like the plague, although the plague was a bubonic plague. But you could have an outbreak of smallpox and wipe out half the population of an area. So smallpox was really bad and feared throughout the Middle Ages. But one thing somebody noticed was that milkmaids that get milk from cows never seemed to catch the smallpox. What was happening is the milkmaids were contracting the cow's version of smallpox called cowpox. But the cowpox and smallpox antigen looked exactly alike. So this guy, a very smart doctor, noticed this, and when he found a maiden that had cowpox, he extracted some pus from one of her wounds and injected that into an 8-year-old boy. Now, later on, smallpox epidemic came through, and he found that the little boy did not get sick. Now, when he injected him with the cowpox vaccine, or the pus from the cowpox, the kid did get a little sick, but it was just fever and chills, and he goes away. So that was actually the first recorded incidence of using a vaccine. The antibodies that we are using for COVID are more complex than that. They're mRNA vaccines, and they actually work with the RNA of your cell. But the way vaccines basically work is we take something that looks like the bad thing. Let's say polio. We take something that looks like, we take polio or dead polio or something that looks exactly like polio, and we inject it in the body so that the body then creates the antibodies against that pathogen. So if you ever contract the real polio, your body is already set up to defend against it. I may be oversimplifying this, but does anybody have any questions on that?
I have one question.
Sure.
So how does it make more if you're taking out dead? Because you said pus is dead cells or dead.
Yes. In this case, when the doctor took the pus from the milkmaid who had cowpox, you had neutrophils that had died, but they still had a lot of the antigens in that pus. So when he inserted that pus into the 8-year-old boy, those antigens were released in his bloodstream, and that triggered his immune system to create antibodies against the cowpox. Now, a lot of times, a lot of our vaccines, what we do is we take a disease and we basically kill the disease. So, for example, I don't know if polio does it this way, but with polio, say, we actually take live polio cells that are dangerous and we kill them. So after we kill the polio, it still has the antigens on it. And then we inject that into the individual, and your body launches an immune response against the polio. So if actual live polio ever comes by and enters your body, you already have an immune system and antibodies to fight it. Now, these antibodies can't last forever. And that's the big issue we've been having with COVID, is they were saying, how long do the antibodies last? For example, I got a polio vaccine when I was a child. Those antibodies are good for life. But with COVID, we were finding that antibodies in the body began to decline over time. And they were worried that, okay, if the antibodies go away, what are we going to do? You know, you don't have an immunity to COVID anymore. And that was a really big worry. And that's where the new COVID vaccine was really innovative, because by using actual messenger RNA and inserting that into the body, it creates a more permanent immune response. And any questions on it? Did I answer your question?
Yeah, that makes more sense.
Okay. there have been a lot of vaccines where we basically just take the live pathogen and kill it and then inject it into somebody and you launch an immune response against it. That didn't work too well with COVID though. They had to get a lot more sophisticated on that. Now, after kind of falling back again, the B cell also has, there are memory B cells. And the memory B cells are basically just libraries. They're the ones that remember the pathogen. And if you get infected with that pathogen again, this alerts the plasma B cells to start producing antibodies again. So we don't have a whole lot of antibodies running around in our body at one time. Usually something will trigger the memory B cells to tell the plasma B cells to start producing antibodies. Clear as mud. Moving on to T cells. One thing may be reflected on the test. B cells are manufactured and T cells are manufactured in the bone marrow. The B cells will mature in the bone marrow, but the T cells go to your thymus to mature. That's easy to remember. T cell, thymus. They both start with T, right? Got it. Now, the T cell has a few more different cells. And like I said, this can get really confusing when you break down all of the different subcells of the B cells and T cells. But the T cell is the one that receives the information from the dendrites, or the dendritic cells. Not dendrites, that's a nerve. The dendritic cells. And they produce helper cells, which assist in the body launching an immune response, and a suppressor cell. The suppressor cells, the purpose of the suppressor cell, well, let me fall back again. The helper cells, these are the ones that recognize the antigen. Remember I said the dendritic cell will come and give information to the T cell. This is where it gets a little confusing. The T cell says, oh my God, we have another attack of this pathogen, smallpox. Okay, it goes to the helper cell, and then the helper cell runs over here to the B cell and tells the plasma B cell to start producing antibodies. So there's a couple cells there that can talk to the plasma B cells and say, hey, start producing antibodies. So the helper cells basically just help the B cell to produce antibodies. Now the suppressor cell, when the smallpox is gone and the disease is gone, we don't want your body just producing more and more and more antibodies. So the suppressor cells say, oh, wait a minute, stop, quit producing antibodies. So the suppressor cells run around, and when they figure out that the disease is no longer a threat to the body, it'll tell the B cells, okay, quit producing antibodies. So this is almost like an on switch and an off switch. It's a way of thinking about it. Now, the T cell can also produce cytotoxic cells. Cytotoxic cells are killer cells. And they're very much like the natural killer cells we talked about in the innate immune system. And they will target mostly cancer and viruses. So they are very important when it comes to diseases like smallpox and COVID, because these are the guys that go after those pathogens to kill them. Mostly T cells hang out. I think this is humoral system. B cells kind of hang out in the bloodstream. The T cells kind of hang out in your lymph system. Not really important, just information for. So important things to remember. B cells produce antibodies. That's why B cells are so important. Without B cells, we would not have an innate immune response. And remember that T cells mature in the thymus. Ta-da! Moving on. So there you go. Those regulator cells and cytotoxic. The regulator cells. Okay, I need Oh, okay, never mind. Going back. Okay. The chart kind of confused me there for a minute. You got the regulatory cells, which break down into the helper cells and the suppressor cells. And then you have the cytotoxic cells, which are also called effector cells. And those two names are pretty much synonymous there. You actually go from an effector cell to a cytotoxic cell, but who cares, right? So there you go. Any questions on the adaptive immune system? No. Well, I must be doing a good job. One last thing before we depart. Hey, we're at a half hour. That's good. I usually go over that. Immune systems, different type of immune systems. You have the naturally acquired immune system. This is what your body naturally does. If you get the measles, if you get chicken pox, unfortunately, if you get smallpox or you get polio, you will also develop an immunity to those diseases. Unfortunately, with smallpox and polio, you develop an immunity if you survive it, if it doesn't kill you first. But when I was young, back when I used to, walk to school 5 miles uphill in the snow both ways, they used to have a thing called measles parties where somebody's child on the block would get measles. And all the other families would bring their kids over to that kid's house to deliberately contract measles so they could get their immune system active against the measles. They used to do that with chicken pox too. We don't do that so much anymore because we have a vaccine against measles and chicken pox. So it's a little safer to do it that way than to have measles parties. But you may hear your parents talk about measles parties sometime. A second type is when we actually get the vaccine. Now here again, this is an artificially acquired immunity because it's artificial, right? We faked it. And this is where we usually take the dead pathogen and inject it into your body to make your body create an immune response against it. Now there's one other, and that's called passively acquired immunity. And that is when a pregnant mother passes that immunity on to the baby. This is usually temporary, doesn't last very long, then the child has to develop their own immunity. But it's just nature's way of protecting the baby when they're first born against any pathogens that may be running around. So for a very short time, the baby will have the mother's immunity for a little bit. I don't know specifically which diseases it does that with. I'd have to look that up. One important thing to remember is as we get older, our immune system, like the rest of our body, starts to tire out, and vaccines don't work quite as well as they did when you were younger and stronger because your immune system is a little weaker. So vaccines may be a little less effective in the older generations. I don't believe that's happening with COVID, thank goodness. But then again, like I said, the COVID vaccine is kind of a different animal because it's using messenger RNA rather than just dead antigens as the method of acquiring immunity. Anybody have any questions on those? That's it. Any questions on the entire material?
Not yet.
Not yet. I will
You're
stop.
ready.
I'll stop the recording at this point.